Hello everybody. Thank you for joining. Bonjour à tous. Falls noch Deutsche dabei sind, auch guten Abend. Wir treffen uns. Oh, I have to switch to English again. We are meeting today because we want to look at the effects of large language models to the education sector and to expert systems, and what can we do to make the most out of the current possibilities. I will share my slide. And we are focusing on expert systems using AI in business processes with the help of NLP techniques. And yeah, we have been, a second, it stops again. Oops. Oh. We've been founded this January, actually, as an NLP provider. So the assistance programs that we develop are developed together with our customer according to his requirements and wishes. That means the expertise needs also always to come from the client. We provide the technical knowledge on our side, and together we can then build a software assistant that supports the client's work. Short outline in the beginning. I will start with what we do at Eloquest and how we used an expert system to approach a very specialized topic together with Nitrexo, the digital engineer, and then Ted from Nitrexo will take over and describe what kind of other use cases there might be with large language models. I will not go in detail regarding large language models itself. They are in the press for quite some months now, so I assume everybody knows it's a language model. They predict the next word, and it's currently very well functioning with Chat-GPT and also GPT-4, which, well, GPT-4 is multimodal. But what is an expert system? So an expert system implies that it's not only relying to machine learning techniques and data analytics, but that we put expert knowledge into a system. So this means when we start from the top of this triangle, we have a client or an expert, generally speaking, who provides user decisions and data input from his domain, his industry, and can interact with a web UI or wizard, and can in this way interact with rules and a business logic that we have implemented inside a software program. The deepest layer then is artificial intelligence. That can mean that we use large language models or data analytics or machine learning approaches. So we use it as a toolbox. But the upper layer is always what the user and what he wants from a system. We especially use this in regulatory affairs. Regulatory affairs means that people have very specialized documents for regulatory affairs that follow strict standards, and they are very well-paid persons who sit there on their desks and just write for plenty of weeks to craft a document that follows all the standards that are needed in his specific industry. And if you are able to automate sub-steps during that process, you can save, well, sometimes up to 70% of the time the human writer would need for the creation of a first draft. If you can automate sub-steps with a software solution, you could also tackle staff shortage, because as currently plenty of people are in their 60s and are leaving the work field, we have trouble, or plenty of companies have trouble to find new skilled workers, and having automated sub-steps could could make this problem a bit smaller. So from our point of view, the typical situation on client side would be that there's an elaborate and therefore expensive writing process with subtasks that need to be repeated over and over again, that there are redundant work steps, and this makes the person who is working on the document slower and prone to careless mistakes. There's also a dependency on specialized personnel, which makes it an urgent issue to find more talented young people. Also, a typical problem of our clients is that out-of-the-box solutions such as Chat-GPT are not, do not work well because either there's not enough expert knowledge included, or the solution needs to be traceable, so explainable. If authorities read a report, for example, about how a drug was tested, they want to see why certain conclusions were drawn, not just read some nice text. But why do we sell that as expert systems, as customized solutions? The issue with expert systems is that not all documents are the same. So there are, for example, ESG documents. There are, in the pharmaceutical industry, plenty of very standardized documents. Same goes for everywhere where you have laws that need to be followed. And not all industries are the same. Also, different template standards and demands for control and influence differ from company to company, also from industry to industry. And plenty of the pre-trained solutions work as a black box and leads to the effect that decisions can no longer be traced retroactively. This is not working for regulatory documents because of the reasons I already mentioned. Also, it's usually the case that a client wants to keep ownership of his solution. So he doesn't want his training data to get to the competition, and wants to own the tool, not share it as an open source solution. One example we had with a client is the development of a clinical study report. When you look into the pharmaceutical industry, there are trials for drugs. I assume most of you read or watched about it during the corona pandemic. If you develop a vaccine, for example, you have to do certain trials, and during these trial processes, a bunch of documents will have importance. For example, the clinical study protocol, which in this case is short with CSP, as a statistical analysis plan, and also the figures that you can write down after the trial had happened. These kinds of documents are then merged into a clinical study report, which is then provided to the authorities who say, yes, we take this drug and allow it to be consumed, or we don't allow it. This process usually takes up to 4 months. Sometimes it's only 6 weeks, but either way, our tool can make the process so much faster that it's done in a couple of minutes. You then have a first draft that can be proofread by human beings. A benefit is that the precision is higher because computers don't get tired, and you have maximal control over the decisions of the system in comparison to ChatGPT, where you have to just trust the system because you can't trace back why certain decisions have been made. So overall, for the client, leads this to certain benefits. On the one hand, an increased efficiency because redundant work steps no longer need to be done manually. The scalability is higher because we can support plenty of new human beings who work in this area just because they use the software. Quality control gets simplified because, human concentration decreases after a while, and computer's concentration does not. And this leads overall to a cost reduction through the accelerated process. This is what we do at Eloquest usually, so working with documents. But the reason why we are coming together today is that we had one partnership with Nitrexo, and it's my honor to present this product that came out of this partnership, which is the digital engineer. By the way, talking about ownership, this product belongs to Nitrexo, of course. And it has the noble goal to make education accessible for everybody. In this case, education about how to build a satellite from scratch. So, of course, because we live in 23, I asked Chat-GPT how to build a satellite just so that we have the comparison. And it told me that building a satellite from scratch is a complex and challenging process that requires expertise in various fields such as electrical engineering, mechanical engineering, computer science, and aerospace engineering. The general steps are determining the purpose, designing the satellite, choosing materials, assembling, testing, and launching. It is recommended to work with a team of experienced engineers and scientists. Looks like a nice piece of text. However, it does not really teach me how to build a satellite. And my computer is a bit slow again. 1 second. So here we are again. So Nitrexo decided to build a platform which is supposed to teach engineering students to build a satellite from scratch. We developed a chatbot that guides the user through her learning experience. Even though there's very specialized domain knowledge, even Google and Chat-GPT is not able to provide us usually with that specialized domain knowledge. We built a database during the course of the project with the help of experts from Nitrexo, and thereby built a product where possible user questions can depend on the exercises. Though it's not only an NLP-focused product, there were also people who automized certain subtasks and designed tasks, exercises for students who would then be taught how to build a satellite. So as you can imagine, there was strong collaboration between software and engineering team needed throughout the course of the project. And Eloquest, back then we were part of L1, would not have been able to do so. Also Nitrexo, hopefully, because they lacked the NLP knowledge. Also Bruce from National Space Center in Ireland joined the group. I just mentioned that because he's on the guest list today. And I try to reach my next slide. Yeah. So reasons why we could not rely only on large language models is the specialized knowledge. Also, some pieces of that information are not Googleable. Also because they depend on dual use regulations between different countries. And this is therefore a perfect example for an expert systems, although it's a learning environment and not a document. We need expert systems when we need control, and also when we can't rely on a user who knows how to prompt. In this case, this means that if I don't know how to build a satellite from scratch, I don't even know where to begin. So it demands a certain amount of expertise to ask the correct questions. And if I don't know that yet, it's impossible to just use a large language model and ask something. We need to know where to start. And also, we need expert systems when we need to stay explainable. That's it from my side. Merci à tous. And I give the word to Ted from Nitrexo. By the way, if you have some questions in the meantime, just feel free to ask.
Maybe, yeah, you want to go ahead and answer that question?
There was one question. Are LLMs and expert systems fine-tuned according to the use case or just based on the initial pre-trained model? They are fine-tuned always. Well, not always. If it's just about general language, goodbye, good evening, and all that, then you can rely on a large language model. But in our cases, it's always fine-tuned. That's it from my side. Go ahead, Ted.
Okay, great. Thank you so much for that, Sarah. So I suppose what I'm hoping really to do in this little maybe 15, 20 minutes or so is to really, I suppose, put forward a vision for what a digital assistant for MBSE activities looks like, particularly using the really incredible new technologies that have really come online and into popularity over the last 6 months. Really, it's been such a short time, and it's incredible what these large language models like Chat-GPT and all of the other ones are doing to really disrupt how we work. And in the space industry, there's absolutely no difference. It really is going to change how we develop spacecraft going into the future. So just quickly before jumping into that, give you a little bit of a background on who we are. So at Nitrexo, we have an expertise in thermal, mechanical, and space systems engineering, and we make those that knowledge and services available to the space community and work with lots of new space companies. I suppose our heritage in the kind of NLP AI domain is, as Sarah said, developing this digital engineer, which was backed by the European Space Agency. And really, I suppose that gives give a platform to onboard engineers, and allows, I suppose, a platform that can be adapted to the needs of the company or the community of learners. And really, one of our core visions is that we believe in the democratization of knowledge and competency, and technologies like LLMs really make that a possibility. Okay, so I'm going to ask for a little bit of audience interaction here. So just to, I suppose, gauge, I suppose, people's understanding of the topic. So I'd love, so we have the hand raise function on the top bar there. I'd love just to get a little bit of an indication. So if I was asking you to raise your hand if you have heard about MBSE before, if you have heard that acronym, if you know what it means. So if you've heard of MBSE before, maybe give your hand a raise. So I've got 1, 2. Okay. So no, that's absolutely fine. So I suppose I've put a couple of slides together to kind of run through what MBSE is, and then go into, I suppose, how we make spacecraft, right? So when we talk about MBSE, so MBSE stands for Model-Based Systems Engineering, right? And when you hear Model-Based Systems Engineering, you might think, well, as engineers, we've been using models for a long time now, right? We've been building structural models, physics models, simulation models, behavioral models. We have been using models in engineering for quite a long time now. And so what's the difference, right? So one of the differences is that this practice, the way we have been doing engineering, really relies on standalone models. So you'll have your FEA model, which will be your structural model. You have your thermal model to understand the thermal behavior of your system. And these are all independent models and often very discipline specific, so mechanical, electrical, thermal, so on and so forth. So, and they then get loosely described in documentation. And so much of the learnings of those models is communicated among documents between many different engineering teams. And you know, you get text diagrams and spreadsheets that really describe these models. The challenge with this approach is first of all ensuring consistency. So ensuring consistency among all of the documented models that you might have, especially as the design evolves, and you know, with large complex space projects, there are lots of evolutions of the design, and it's, you know, it's typically a multi-year process. So that's one challenge. And the second then is just getting a system level understanding of the technical baseline. Having a massive stack of documentation isn't necessarily, doesn't make the job of, you know, a new engineer coming on board, or a new, you know, partner coming on board and trying to engage with the project. It makes that that process quite difficult. So what's the difference in MBSE? So MBSE is a definition given there by INCOS, who are kind of um, a professional organization who really drive systems engineering innovation. So MBSE is the formalized application of modeling, support the engineering activities that systems engineers always engage in. So that's namely requirements management, design, analysis, and verification and validation. So MBSE really begins early in the project lifecycle and continues right through the entire design phase and into the testing phase. So it's worth noting here as well that the system model is both human readable and computer readable. And therefore it makes it more easy to check in automated ways for completeness and consistency. And this is really the crux of where we can really leverage LLMs. So really what we have when we have an MBSE model, it becomes the basis of communication at a systems level, for not just for the humans to understand the evolution of the design, but also for integrating information across the discipline specific model. So it really becomes, if you use one phrase, the single source of truth. And that's really the goal of any model-based systems engineering approach. So in terms of so MBSE isn't really widely adopted throughout the industry just yet. As an industry, we're really going through a transition phase. So I love the little diagram down in the bottom right there. It kind of uses the analogy of a Lego man to describe. So the traditional approach is document based, and the place that we're getting to is model based. And there's all these, it's not a binary scenario, right? There's all these different stages we go through. And some organizations are very far along that and are fully adopted to MBSE approaches. Others are halfway there. Others not at all. So the transition from document-centric systems engineering to model-based is really well and truly underway. So ESA, the European Space Agency, has been promoting the MBSE approach for many years now. In particular, at the moment, there's a very good initiative called MB4SE, so model-based for systems engineering, that seeks to accelerate that adoption again. Because essentially they recognize the value in streamlining the design, the development, deployment, and verification of space systems. It's really, you know, the value of this approach is well identified. So within the MB4SE activity, ESA have defined several user needs that really cover a broad range of needs. So first one we'll say managing increasing complexity of space missions is really a core need. Supporting compliance with best practices, ensuring consistency, completeness, and feasibility of requirements and design, and ensuring stakeholders and non-MBSE proficient users in understanding the system design. That last one I think is really important as well. So I know that we just had a question come through there, so leave me just, so that's just Ahmed saying you have to leave. That's no problem, Ahmed. Thanks for joining us.
I can have
Okay.
a look at the questions so that you don't have to focus.
Okay. Thanks, Sarah. Cool. So in terms of MBSE user challenges, so MBSE puts forward a great value proposition, but particularly in how we're using it at the moment, there's certainly some challenges that still need to be overcome. So the first is managing model complexity. So spacecraft are highly complex systems, and those system models are complex in themselves. So this becomes challenging to manage, especially as you have interoperability between different subsystem models. So you might have a propulsion model, a structural model, a thermal model, system models, and interoperability between those can also be a challenge where they're using different tools or methods or best practices. Another user challenge is verification and validation. So MBSE requires extensive testing and validation to ensure that the models accurately reflect the spacecraft system. And that in itself is a challenge to achieve, where, especially in the space environment, where the testing opportunities are limited and often very expensive. Third, then, is really the culture shift. So MBSE requires a shift in the way that engineers think about systems engineering. We're really taught a document-centric approach, and that's the way it has been done. So moving to a model-centric approach requires a significant culture shift. And that's something that's been found to be challenging for engineers in organizations that are more used to the traditional approaches. And lastly, then is model management. So spacecraft systems are typically developed over long periods of time, near decades in some projects. And models used in MBSE can become outdated and inaccurate if those models haven't been managed effectively. So this is the task that engineers need to do. They need to manage these models carefully to ensure that they remain accurate and up to date throughout the design process. So they're kind of picked out 4 kind of key challenges that we're still facing within MBSE at the moment. So we have a new way of working in terms of MBSE and all of these MBSE tools here on the left. And really, we have a new generation of AI assistants and technologies coming on board. And really, what we want to explore and set out a vision for is how do we marry these two technologies? How do we take, how we're going to design and build space systems in the future, and these new really disruptive technologies. How can we use that to benefit how we build space systems in the future? So the first, I suppose as well with these use cases of, even if you don't have an MBSE background, I think especially with this first use case, it should be very clear, because I suppose within space projects, you have lots of people coming from lots of different expertise, lots of different stakeholders with different expertise, not necessarily having any MBSE background. So the diagram you have in the front there, so it's a logical architecture. It's essentially defining at a logical level the spacecraft stack, so a typical spacecraft stack. And that sort of a diagram can be quite intimidating, quite difficult to understand and digest, especially if you haven't had any experience with MBSE workflows in the past. So why not use large language models to help us digest and understand that? So using this kind of chatbot format of really interrogating this system diagram, the system model, to help us understand whatever part of the system we're interested in. So the example here we have is why was a loop heat pipe chosen over other heat pipes. So interrogating the trade study that was and the design justification for the model. And so our digital assistant can I suppose pull that information first and make it available. So tell us that the trade study concluded that the loop heat pipes were the best option because of whatever options or whatever reasons. Also, we can, interrogate things. But so the example here is, how does the thermal control system interface with the spacecraft bus? So maybe we want to understand what mechanical links, what electrical links, what communication links there are. So that this sort of an interface really helps us interrogate the system model, especially for stakeholders within space projects who again aren't necessarily fully familiar with MBSE, but still need to be able to understand the design and design justification of a space system. So that's a one use case. The second one, then getting a little bit more technical. So again, as we explored earlier on, big complex space systems have big complex space system models. And really what we want to explore here is trying to reduce the likelihood or the number of errors we have in that modeling process. So here we have an example of a typical mode state machine created during the system analysis stage of an MBSE workflow. So we have, it's a I suppose example spacecraft. We have a pre-launch mode, we have a launch mode, sun acquisition, nominal mode, orbit mode, safe mode, right? And this is just a small subject of a small subsection of a relatively simple spacecraft. But these, if you're modeling a system with maybe hundreds of different modes and thousands of different transitions between those modes, it can get very, very complicated very, very quickly. But actually on the diagram up here, we have something missing, right? So there's a transition missing in this diagram, and that's very hard to troubleshoot, even on a relatively small diagram. But if you scale that up to the hundreds of modes and then thousands of transitions, it gets even more difficult. So we can use large language models to help us identify that. So in this scenario, what we actually had missed there was any means of getting from a safe mode back to a nominal mode. If we got into safe mode, there was no possible way for us to get back into nominal mode. And so what can appear like relatively small modeling errors here really have significant impact on the projects if they're not picked up early. And when the diagrams are in the hundreds or thousands of different modes and transitions, having a tool to allow us to help troubleshoot them and debug any errors is of real value. The last example here I'll go through is in terms of requirements compliance as well. So, in your typical space project, you'll have hundreds, thousands, maybe even tens of thousands of requirements that you have to comply with. And it is a real challenge for systems engineers to do that. So the example requirement I give here is just so in this case, we're designing a rover, and the rover needs to have hazard detection and avoidance capabilities. And in this instance, I haven't actually modeled the requirement compliance. So I've asked the system, am I required? Am I compliant to user requirement 70? And no, I'm not, because I haven't made any model correlation or model link to it. So I'm not compliant with this requirement. But we can also ask how can we comply with this requirement, right? So the system can then tell us that the system is missing functionality to perform hazard detection and collision avoidance capabilities or functions. So, and then we can then model that and make sure that we're modeling a system function to perform hazard and collision avoidance maneuvers, which allows us to then comply with that requirement. So again, on one requirement, this can be quite simple, but when you have to manage hundreds, thousands, tens of thousands of requirements, having a tool that makes sure that helps you make sure that you're fully compliant with your requirements is of real value. So that was, just a quick brief overview of 3 different use cases that we could really utilize LLMs, large language models, to assist in how we're going to build the space systems of the future. But I suppose we also always need to be aware that there are limitations in any technology, and large language models are no different to that. So we have challenges in terms of domain-specific knowledge and data. It is very difficult to get data particularly in the space industry. It's very domain-specific. So yeah, limited ability to handle technical jargon. So we also have a need for specialized data to do further training. Everyday language is not sufficient. So really, this all boils down to the data. Getting our hands on space data is certainly a challenge. Additionally, I think Sarah mentioned this earlier, but in terms of lack of control, so the black box solutions make it difficult to track back why certain decisions have been made. So we can interrogate our system model because it's we can look at it, we can interrogate it, but a large language model we cannot really interrogate why it's made the decision that it's made. And I think really in all of this, engineers or humans are definitely still the best engineers we have. I don't think AI is going to take my job just yet. But really, in terms of these tech and in terms of utilizing the current generation of large language models, what we really need to focus on as a philosophy is to assist and not try to replace the engineer. I think that's where we're going to extract the best value. So yeah, that's I suppose a brief overview, a quick vision for how we're going to use large language models for space systems engineering in the future. And yeah, happy to answer any questions.